Hello students, and welcome to chapter 5, Introduction to Limit Theorems. In this chapter, we will explore one of the most powerful ideas in probability and statistics, how sequence of random variables behave as they converge over time. Those concepts form the mathematical background of data science, statistical inference, and machine learning. Whether we are analyzing estimators or modeling uncertainty, understanding convergence is a key. We will begin with almost sure convergence, which is the strongest form of convergence. Through a simulation of 10,000 coin flips from a Bernoulli distribution with mean 0.5 distribution, we will observe how the sample mean stabilizes at 0.5 as the number of tails increase. An illustration of the strong law of large number, where deviations eventually vanish. Next is convergence in probability. Consider a noise sequence of the xn, which is equivalent to the population mean mu plus the sequence zn over square root of n, or sample size, where randomness disappears over time as n grows or infinity. Initially, the sequence fluctuates, but as an increase or grow, values begin to cluster tightly around the population mean mu, showing that the probability of large deviations goes to zero. This behavior captures the idea that outcome becomes increasingly reliable, even if individual paths are noisy. Then we transition to convergence in distribution to demonstrate through the central limit theorem. By simulating standardized sample means from uniform or exponential distribution at various sample size like 5, 30, and 100, we will see how they begin to resemble as a perfect bell curve. Regardless of the original distribution, the limiting distributions of the sample mean approaches to normal distribution or Gaussian, demonstrating the universality of the central limit theorem. We will also explore mean square convergence, where the average square error between sequence and its limit x, or observed value, shrinks to zero. In our simulation, in the sequence xn, which is equivalent to observed value x plus 1 over n, or sample size, converges to x is equals to 0 in mean square. The mean square error curves, which is 1 over n square, decays rapidly to 0, confirming theoretical expectation. Unlike convergence in probability, this mode ensures not only real but also a small average fluctuations, which is vital in application like optimization and signal processing. Finally, we will revisit the weak law of large numbers using the die rolls. When rolling a fair die with expected value 3.5, we will track how the distributions of sample means behave across different sample sizes. With a small sample size, n is equals to 10, the means are scattered. But as we increase the sample size to 100 and then 1000, the distribution fluctuates around 3.5, forming a bell-shaped curve. This is not only reinforces the law of large numbers, but also aligns with the central limit theorem, confirming that even with non-normal data, averages become reliable and normally distributed for large n or sample size. Together, these simulations bring to life the hierarchy of convergence, from almost sure convergence to convergence in probability, and finally to convergence in distribution. This hierarchy is foundational to modern statistics and machine learning, revealing how predictability emerges from randomness. Let us dive in and uncover the mathematics of uncertainty. See you next time.